Okay. Hello. So, we have one more example I wanted to work through in order to look at formal charges. This time, let's go ahead and do sulfate. Okay, remember sulfate is SO4 2 minus. Okay. So let's go ahead and swat up the Lewis structure and then check out formal charges. Okay, so SO4 2 minus, sulfur gives us 6 valence electrons, oxygen gives us 6 valence electrons, times 4 is 24, and then the charge gives us 2 more. So 24 plus 6 plus 2 gives us 32 electrons. Okay, so now we go ahead and put sulfur in the middle. We surround it with oxygens. 4 oxygens, 4 bonds, take up 8 electrons, leaving us with 24. Now we surround each oxygen with valence electrons, or non-bonding pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And that uses up all of our electrons, leaving us with 0. So each oxygen now has 8 electrons, and our sulfur has 8 electrons, so it is happy. We have no electrons left to use up. So we go ahead and we put brackets around it, indicate that it has a -2 charge, and say we're done. But let's go ahead and take a look at formal charge. Okay. So each oxygen starts with 6. And so does our sulfur. Now, how many electrons does our oxygen see? 2, 4, 6, 7. So each of our oxygens, they look exactly the same here, so they're all going to have a -1 formal charge. I can write. Okay. Whereas our sulfur sees 1, 2, 3, 4. So 6 minus 4 equals +2. This is actually an awful, terrible, no good piece of crap Lewis structure, because you have a +2, you have 4 -1s, you have charge separation, as it's called, when you have different numbers like that, a positive and negative right next to each other, and you have a 2. You never want a 2, if at all possible. Get rid of 2. You want zeros. Okay, 0 formal charges is better. So what you can do to change that is you can convert non-bonding pairs into double bonds. And every time you do that, this is what happens. Okay, so sulfur and oxygen. Now this oxygen has 6, 2, 4, 5, 6 minus 6 equals 0. And sulfur's charge went from 6 minus 4 equals +2 to 6 minus 1, 2, 3, 4, 5 equals +1. Okay. So oxygen's formal charge went from -1 to 0, making oxygen happier, and sulfur's formal charge went from +2 to +1, making it happier. Okay, so no wonder I've been using that. Okay, so you can do that again, in fact, to make sulfur even happier and make an oxygen happy. So 6 minus 6 is 0, and 6 minus 6 is 0. Okay, and then of course you're going to have 2 oxygens, one on either side, with formal charges of -1. And oxygen is above sulfur, so oxygen has a higher electronegativity, so it should have the negative charges, so that's all right. Not only that, but -1 plus -1 plus 0, 0, 0 gives us a total formal charge of -2, which matches the total charge of our molecule, and that is the actual Lewis structure of sulfate. And what happens after that is that if you drop it in water, it will react with water. Oops, there should be extra non-bonding pairs. I'm sorry. One of you should have called me on that. Next time, raise your hands. All right, is that you'll react with water to form bonds like that to form H2SO4, or sulfuric acid, with a 0 formal charge on every single atom. All right. So anyway, that is why sulfate is the way it is. That is the way it is, and that's why. Is what I should say. All right. So hopefully you at least understood how to do formal charges and Lewis structures. Practice, 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 practice. All the time with the practice. Oh, and once again, it doesn't matter which 2 oxygens you choose. They're all exactly the same. All right, so moving on. We already discussed that. Resonance. Okay. Resonance, we've already discussed a little bit in talking about, for example, why silver only takes a +1 charge. It's because when you have things that look exactly the same, they look around them, they see things exactly like them, and that makes them happier, that makes them more stable. And you get the same thing with Lewis structures. So let's make a slightly simpler image. Let's go back to looking at carbonate, okay, CO3 2 minus. Recall perhaps that carbonate has oxygens like this. And I said that time that it didn't matter which oxygen you chose. And that is still absolutely true, because what actually happens is that you get resonance. And let me shrink this down a bit. Okay. Meaning that this double bond does not exist just on that oxygen. Instead, you get that, and you get this guy down here. Okay. So you get these 3 structures, okay, existing simultaneously. The double bond is on all 3 oxygens at the same time. Okay, if this is bond A, and this is bond B, and this is bond C, okay, then bond A is 2/3 a single bond plus 1/3 a double bond. Okay? And B is 2/3 a single bond and 1/3 a double bond. And C is 2/3 a single bond and 1/3 a double bond. That is what resonance means here. So what we do, in order to draw the Lewis structure of carbonate, we have to draw all 3 of these pictures and draw these little double-headed arrows to indicate that it's constantly flipping back and forth randomly between all 3, or, to say it even better, all 3 exist simultaneously and to the same degree. So you see resonance a lot, okay, but you can only see resonance if you have double bonds, okay, or triple bonds, multiple bonds, I should say. If you have a multiple bond, at least one, then and only then you can get resonance. And that is a pretty big deal. So for example, in organic chemistry and biochemistry, you'll see something like this. Okay. This is a carboxylic acid. Carboxylic acids are huge. They're everywhere in organic chemistry and in biochemistry. For example, this R is just sort of a variable. It's a placeholder. It could be, pretty much anything. It could be just a hydrogen. It could be a long carbon chain. It could be a dog. It could be anything. But if that R is actually, let's see, a CH3, then this is acetic acid or vinegar. Okay. Whereas if it's just a hydrogen here, then this is formic acid. It is the thing that ants use to make their bites sting like the dickens. Right. So that's what R means, and that's just 2 examples of these carboxylic acids in nature. And the reason they are acidic is because of this hydrogen right here. It can, go flying off to become H plus, an acidic proton, as it's called. And what will happen is it will leave behind this, okay? An oxygen with 3 non-bonding pairs and a negative charge, and another oxygen with 2 non-bonding pairs and a double bond. But now you have 2 oxygens, and why would you have a negative oxygen here and a double bonded oxygen there? There's no particular reason to leave it like that. You get resonance. Okay? So R bonded to C, bonded to oxygen with a negative charge, and double bonded to the other oxygen. And so you get something, you get these 2 pictures, flipping back and forth constantly. They exist simultaneously. So you have resonance. Okay? The actual structure of this carboxylic acid is sort of a double bond smeared across between these 2 oxygens, each one of which is sort of sharing in the negative charge. And so because it's resonance, that makes it happier, that makes it stable, and that's why carboxylic acids are acids. That's why this hydrogen over here is free to pop off and become an acidic proton. And that is what lets these carboxylic acids function in the way they do. And because they're acidic, that's why they show up all the time in organic chemistry and biochemistry. It gives them that function, that flavor, and lets them do the things that living organisms sometimes need them to do. So resonance is a big deal. You're going to have to get used to it and remember it, and keep your eyes open for double bonds, because if you have double bonds, you can have resonance. You don't always have resonance, but you can. Okay, so for example, carbon dioxide has double bonds, but it doesn't have resonance. Okay, because that's difficult to read. Okay, so because when you look at the formal charges, 0, 0, 0, everybody's perfectly happy in carbon dioxide with those 2 double bonds. So no need to change. It doesn't change. Okay? Or at least any possible resonance is so minor and effervescent that it just doesn't contribute in any real way to the overall structure of carbon dioxide. Whereas if you look at, say, going back to carbonate with its 3 semi-demi bonds, these bonds are all exactly the same. Whereas if it didn't have resonance, one of them would be a double bond, the other 2 would be single bonds, and you would see one of them would be different from the other 2. So resonance does play a big role in the actual structure of these molecules. So keep your eyes open. Look for possible resonance. So that does it for drawing Lewis structures and talking about molecular structure. Well, not entirely. I mean to say that we've gotten as far into molecules and their shapes and structures as we can. Next time we will start talking about geometry. For those of you who aren't good at visualizing in 3 dimensions, I do apologize. There's really no help for it. I will try to help you find ways to cope, but geometry is really important for chemistry. It has a huge impact on the way molecules behave and interact and react. So just grin and bear it. Find a way to work through it when we start getting on to our next set of slides and start talking about molecular geometry.